Now we would like to derive the Euler-Lagrange equations of motion for the classical field. So we're going to start off as usual, and we are going to say that the solution, um, the solution to the classical equations of motion minimize the action S. Okay. So that's always the starting point of the Euler-Lagrange sort of approach to mechanics, to Lagrangian mechanics. So what is the action? Well, the action was given by the time integral of the Lagrangian. We can go from some initial time to some final time. And we said that, in fact, we would prefer to work with the Lagrangian density, and let's call the spatial domain of integration V of the Lagrangian density. Now, why did we do that? Let's just remind ourselves dt is not Lorentz invariant, but dt times by d3x is Lorentz invariant. So that means the Lagrangian density is Lorentz invariant, whereas the Lagrangian is not Lorentz invariant. And we prefer to work with something that's Lorentz invariant, so we prefer to work with the Lagrangian density. Now, what will the Lagrangian density depend on? Well, the Lagrangian will depend on the position of the particle and its derivative, so q and q dot. So you might naturally guess that the Lagrangian will be a function of phi and d naught phi. Okay, now that's not correct. And why not? Well, we want to build something that's Lorentz invariant. Even if in my frame things only depended on d naught phi, if I was to boost to your frame, well, d naught phi is just a single component of a 4 vector, and this one component of the 4 vector that I have will mix with other components of the 4 vector. So in your frame, it would depend on d mu phi, all 4 components. And with an I to Lorentz invariance, we know that we should be writing things in terms of 4 vectors and not just a component of a 4 vector. So it is natural and correct to assume that the Lagrangian density depends on phi and d mu phi. Good. Okay, so now what do? Well, we are going to vary the field, and we're going to set the variation to 0. And the requirement that the variation of the action is 0 is going to give us our equations of motion. Okay, so we are going to vary. And this means we will replace phi by phi primed, which is the original phi, but plus some change that we will call delta phi. So we'll vary, and then we will require that delta S is equal to 0. And it's this requirement that delta S is equal to 0 that is going to determine the Euler-Lagrange equations of motion. Now, of course, if we have changed the field, it is clear that the derivative of the field will also change. So the derivative of the field, we're going to do mu phi primed, and this will be the old derivative plus, however, this derivative changed. Now, I'd like to derive an equation for this change in the derivative. So let's start off from the statement of how the field changed. And let's just take a derivative of that equation, okay? So if phi primed is equal to phi plus delta phi, then the derivative of phi prime, the derivative of that function, has to be equal to the derivative of phi plus delta phi. So this must definitely be true. But comparing, you can see that this matches that. Those are exactly the same. This matches that. So the last terms have to be the same as well. And that tells me that the change in d mu phi is equal to d mu of the change in phi. So that's the equation that I wanted. This tells me how the change in the derivative of phi is related to the change in phi. Good. Okay, and now let's talk a little bit more about this variation. Oh, okay, so let me just remove that. Don't need that. Good. Okay. Now, let me just remind you of one thing that I think should be helpful. Remember when we were studying the particle? So what we did, we had T, we had Q. There we specified some initial time, we specified some final time, we had an initial position, and we had a final position. So the particle started from Ti at started from position Qi at time Ti, and it landed up at position Qf at time Tf. And then we said, well, the path is going to be some path between these two. And we considered a whole family of paths, but you can see that importantly, all of the paths started at the initial point, and all of the paths ended at the same final point. And the way that we arranged that is we said the change in the coordinate QFT is equal to 0 at the initial time and the final time. Well, here, when we set up this variation, we are going to say something very simple. We want to specify some initial and final value conditions. So we're going to specify that the field at the initial time and all positions x is equal to some initial field configuration. So let me just call it phi init of x. And we want to specify that the field at the final time and at all locations is equal to some final configuration and at all x's. So in particular, what this means is the variation that we allow when we want to change delta phi, we are only going to consider phi's and phi primes that both satisfy the correct initial and final conditions. So that means that delta phi at the initial time and all x's has to vanish, and delta phi at the final time and all x's has to vanish. This is just because we are specifying the initial condition and the final condition, and we're only varying over fields that obey that initial and final condition. Good. So this is what we needed. We can now get going with deriving the Euler-Lagrange equations.